A2 Rates and Orders Introduction. This video is going to take you from what we know about rates from AS and move on to how and why we use experiments to discover what orders of reaction different reactants have, to show how a mechanism can be built up and how we can actually calculate different orders from data. So at AS, we know that we can speed up this reaction here in 5 ways, each of which increases the number of or the frequency of collisions and the frequency of successful collisions. So we've got temperature, pressure, surface area, adding a catalyst, or we could increase the concentration. Look back at AS if you want to find out more about those. At A2 now, we're going and we're looking at specific components. We're saying, okay, let's do an experiment. Let's hold A and B constant, and let's have a look at, if we change the concentration of C, how does the rate change? That's what we call the initial rates method. We do a lot of different experiments holding everything the same but the concentration of one of the components. We do this to find out more about how each of the components affects the rate of reaction, and we can only do this by experiment. And these experiments often lead to the proposal of a mechanism for the reaction. So my proposed mechanism for this reaction, for example, is this one here. I'm going to say that maybe A plus 2B gives me D, and D plus C then gives me E plus F. D, of course, is made and then used up in this reaction, so it's begins with I. It's an intermediate, that's it. So here I've got a possible mechanism, but I can't find anything out about whether my mechanism is correct without doing an experiment, an initial rates experiment, where I'm going to hold these concentrations the same and alter C. I'll also then go and alter B, holding A and C the same, and A, the concentration of A, holding B and C the same. What I'm looking for is which of these steps is what we call a rate determining step. Which of these steps is a fast step? Which of these steps is a slower step? If one of them's really fast, it won't matter if that step gets speeded up. If one of them's really, really slow, we want to speed that up, otherwise the whole reaction will be slow. Looking at this in a different way, say here that I decide to go on a trip. I want to go from Rochdale to London to Lhasa. But my problem is that going from Rochdale to London, I've got to walk. From London to Lhasa, obviously, I'm going to fly. Now walking probably here takes, what, 2 weeks? Maybe. Flying, maybe 8 hours. It doesn't really matter which flight I get from London to Lhasa. Maybe it'll take 4 hours, maybe it'll take 10 hours, 12 hours. If it's taken me 2 weeks to get from Rochdale to London, it doesn't matter what flight I get. This is the slow step that I've got to speed up if my whole reaction, if my whole trip is going to go faster. So we do these initial rates experiments to find out which part of the reaction takes longer. Here's a set of results from an initial rates experiment. You can see that I've got the concentration, square brackets mean concentration of A, B, C. I've got a rates column, so this is the rate when these concentrations were added together. This was the rate of reaction. And I've got a number of different experiments that I've done. This is the normal, well, it's often the way that data is presented to you in the exam. And what we're going to do is just go and have a look at how the concentration of A has affected the overall rate of reaction. So looking first at the concentration of A, in experiment 1, everything's got a concentration of 1 and we've got a rate of 0.5. What I've got to look for here now is where A changes. So here I've got a concentration of 2. So A is changed from 1 to 2, but I must ensure that everything else is the same. So B in experiment 1 is 1 and experiment 3. So that's the same, that's good. Experiment C is 1 and experiment 3 is 1. So I'm going to use the data where I can see that A has doubled, but B and C have remained the same. So from experiment 1 and experiment 3, I can see that just trying to sort my pen out here. I was hoping to have a highlighter and I didn't get one, and now it won't let me have a pen. From these two experiments here, it's typical, isn't it? These two experiments here, I've had an increase of 2. I've doubled my concentration. And notice how my rate here has gone from, oh, that's useful, isn't it? Hold on a minute. So here we go, bit better sorted out now. So looking at concentration of A's doubled. B has remained the same in experiments 1 and 3, and C has stayed the same in experiments 1 and 3. Here we can see the rate has gone from 0.5 to 1. Remember, this is experimental data, so there might be a slight variation, but essentially 0.5 going to 1 is also times 2. So when I double the concentration of A and B and C stay the same, my rate is also doubling. So what we find is that the concentration of A and the rate are in a proportional relationship, so that I could say that from experiment 1 and 3, I can see that as A doubles, the rate doubles, and here we get an idea. So the real order is first order with respect to A. That is, it's directly proportional. As you double the concentration, you double the rate. And that's what first order means. If you double the concentration, the rate of the reaction will also double. Let's have a look now at the concentration of B. Looking at B, we've then again got to find where B is doubled. So we're going to be using experiment 4 because B is doubled. But then we've got to find the other experiment where A and C remain the same. So here, in fact, in experiment 3, we've got B going from 1 to 2. We've got A that's 2, but it's staying at 2 in experiment 4 too, so that's okay. It's staying constant while I'm doubling B. Here, C is going from 1 to 1, so that's staying the same. So I can use experiment 3 and 4 to look at how the concentration of B affects the rate of reaction. And here, so if I've got my highlighter being nice to me, no, it's not going to, is it? Well, I'll underline it anyway. So I've got experiment 3 and experiment 4. And what we can see from here is that as I times the concentration of B by 2, if I double it, it goes from 1 to 2, I'm timesing it by 2, then the rate of reaction itself goes from 1 to 4. It's times by 4. Now, what we can say about the effect of B on the rate of reaction then is that from experiment 3 and 4, and it is important you say which data you're using, B doubles, the concentration of B, remember square brackets means concentration, the rate increases by 4. So this reaction is what we call a second order reaction with respect to B. It's saying that when you double the concentration of B, you do in fact 2 squared the concentration or the rate of reaction. And we'll come back to that in a moment. Now looking at how C affects the rate of reaction, again we look at our data to find where C has doubled, which in this case is in experiment 1 and 2, which is quite nice, and we can see that B has remained constant and A has remained constant. So here we're going to be using experiments. Let's see if my pen works this time. Oh yes, look at that. 1 and 2. And we can see here then that as C doubles, the rate in fact remains the same. There is no change. This case then is where the concentration of C, or the increase of concentration with C, affects the rate as a zero order. In other words, as C changes, it has no effect on the rate of reaction. So we could write that as, using experiments 1 and 2, which remember A and B are constant, only C changes, the rate doesn't change, so the order is zero order with respect to C. That is to say, however much you change the concentration of C, the rate of reaction is completely unaffected. The results overall then, A doubles, rate doubles, so first order, B doubles, rate increases by times 4, so the reaction is second order. It's the amount that the rate doubles squared, if you like, is second order. So if B had tripled, the rate of reaction would increase by 3 squared. And in the final, or in C, when C doubles, the rate doesn't change, and we said this is zero order. Now, since the concentration is causing the rate to change in at least 2 cases, we can say that the rate of reaction is proportional to the concentrations of A, B and C. Now to turn that into an equation, we put in a rate constant, so we can actually have an equation. But then we look at the concentrations and we put them to the power of their order. So A is first order, so A would be to the power of 1, B second order, so it would be B squared, and C is zero order, so 0 to the power of 0. So we get a rate equation that looks like this. And if you're familiar with maths, you will know that anything to the power of 0 becomes 1, and so this term no longer needs to be in the rate equation, and of course something to the power of 1 is simply itself. So our final rate equation looks like this bottom one here. Rate is equal to K, the concentration of A, the concentration of B squared. Now if we return to the mechanism for the reaction, which I suggested was A plus 2B gives D, D being the intermediate plus C is E plus F. We can now have a look to see which is the slow step and which is the fast step. We saw that C was zero order, so no matter how much you increase the concentration of C, the rate will not increase. But crucially, A and B did affect the rate, and they remain in the rate equation. These are the elements that cause the slow step. These are the rate determining step components. So A and B, two molecules of B, here we've got 2B, A and 2B give a rate determining step. So this is the slow step, and this would be the faster step. So that was a whistle-stop tour of the rates topic. Rates at this point is experimental. You need to check how the concentrations of different reactants will affect the rate of reaction. You do that from experimental data by looking at the tables and deciding how they've affected the reaction. You then must put this into a rate equation, and that rate equation will tell you about which components are involved in the slowest step of the reaction. My following videos will be all about how to calculate the different orders of reaction which enable us to build up the rate equation, because that is key for your exam.